Alright guys, this is going to be note card 23 called the chain rule. Okay, so here's what we're going to think of as the chain rule. I want you to think about the chain rule as a blow pop or as a Tootsie Pop. So when we eat a Tootsie Pop, we eat the outside first. And as we're eating the outside first, the inside doesn't change at all. The inside stays the same. Okay? And eventually, as we get down to it, okay, it gets smaller and smaller and smaller. We still have that middle. And eventually we get to a point where we just have that inside part, whether it's chewing gum or whether it's a Tootsie Roll at that point or whatever. So the way I like to think about the chain rule is that we're going to take the derivative of the outside, okay, with respect to the inside. That part doesn't change, and then eventually we're going to get down to here and we're going to eat it all. So times the derivative of the inside. That's the best way to think about the chain rule. Okay. So here's a couple examples real quick. So let me just kind of give you a practice problem. Let's say that y equaled the sine of 5x cubed. Okay. Well, if we follow this process, first thing is we take the derivative of outside. So the derivative of a sine is a cosine, but we're starting to eat the outside. We haven't got to the inside yet. So the inside stays the same. But now, eventually, when we get to the inside, we want to eat the inside as well. So I have to multiply that times the derivative of the inside, which would be 15x squared. Okay, so that's an example of the chain rule in action there. Okay. So the way we approach this is we take the derivative of the outside with respect to the inside. So think about this composition function. We take the derivative of the outside, f prime, but we haven't done anything to the inside yet, which is still g of x. But after we do that, we have to multiply times the derivative of that inside. Okay. So let's see how that works on a couple of example problems. So imagine this said something cubed. Okay. So if we have something cubed, our rule is, so imagine that was like a U. Okay, maybe I'll do this on a spare sheet of paper. So I'm just going to rewrite it. F of x equals x cubed plus 7 quantity cubed. Now you could actually write this 3 times and multiply it and then use your other rules to find the derivative, but that could take a long time. All right, so let's make a replacement real quick. Let's let u equal the inside term. That thing's on the inside. If we do that, now we can just say that f of x is simply u cubed. Okay. If I wanted to take the derivative of u cubed, I would move the 3 out front. Then I would take u and I would reduce the power by 1. But the problem is we haven't taken into account the derivative of this thing. So now I have to multiply times the derivative of u with respect to x. Okay, in other words, if I wanted to find du dx, that would simply be 3x squared, because the derivative of this is 3x squared. Okay, the derivative of this is just 0. So I would have to take 3u squared times 3x squared. But the issue is everything needs to be back in x terms, not u terms. Okay, so I have to resubstitute whatever that u was. That u was x cubed plus 7. Okay. So this would be the derivative of that case. Okay. And if you wanted to rewrite it a little bit nicer, remember multiplication, it doesn't matter what order you do things in. I got a 3 there. I got a 3x squared here. I could multiply those things together first. So if I multiply those things, that would be 9x squared. And then I could write this x cubed plus 7 quantity squared. And that's a better way to write it. Okay. So I'll go over that problem one more time. So we're going to treat this like the inside function. Okay, so if you have something cubed, the 3 comes out front, that power gets reduced by 1, and then you're going to multiply times whatever that inside, the derivative of that inside function is. So that inside function is still x cubed plus 7, but now you got to multiply it times the derivative of that thing, which again would be 3x squared. So let's look at the next problem, number 2. It says f of x equals cosecant of 3x over 5. Don't forget, I can rewrite that. I do not need to use the quotient rule. I can write that as 1/5 times the cosecant of 3x. So when I take the derivative here, notice this is a coefficient, it stays. So I need to do 1/5 times the outside function here is cosecant. Okay. So what's the derivative of cosecant? It's negative cosecant of something times cotangent of something, all times the derivative of the inside function. What was the inside function? It was 3x. What's the derivative of 3x? It's 3. Okay. Now what do we put back in here? We got to keep the inside function the same when we take the derivative of the outside. So those both get 3x's. So if we put all that stuff together and simplify this a little bit, I got a 1/5 times a negative times a 3. That's negative 3/5. Then I can write cosecant of 3x times the cotangent of 3x. And that is the derivative of that problem. Okay, let's look at the next one. Next one's a little bit harder. So in this one, g of x equals x times the square root of 2x minus 3. Now let's write this a different way, so taking a derivative would be easier. Okay, so this means x times 2x minus 3 raised to the 1/2 power. If something's underneath the square root, it's getting raised to the 1/2 power. So what do you notice here about g of x? This is a product. So if I want to take the derivative of a product, I have to use the product rule. So g prime of x, I take the derivative of the first term, which would just be 1, times the entire second term, always a plus what? The first term times the derivative of the second term. I'm just going to write it with Leibniz notation there. Okay. So let's simplify this a little bit. Well, how do I take the derivative of all this? So we have something in parentheses, something raised to the 1/2 power. The 1/2 comes out front, whatever's in parentheses stays there, and that gets reduced by a power. Times the derivative of, we can think about this as the inside. So the derivative of the inside, 2x minus 3, the derivative of that would just be 2. Okay. So this would be considered my first line answer. Okay, now can we simplify that and make it look a little bit better? Sure we can. We have a 1/2 times a 2. Those simplify to give me 1. So let's think about what we really have here. We have a 2x minus 3 to the 1/2 times 1 is itself, plus this right here is getting raised to the negative 1/2 power. So what I can do, I can move that to the denominator and again write it as a positive 1/2 power. And this x in front, x times 1, that would just be x. Now, I can probably simplify this a little bit more. I can get a common denominator. All right, to make these match, I could put another 2x minus 3 to the positive 1/2 on the bottom and on the top. So what would happen if I did that? Well, you have 2x minus 3 to the 1/2 times another 2x minus 3 to the 1/2. So that would just be 2x minus 3. Remember, we add the powers as long as the bases are the same. 1/2 plus another half is simply 1 plus x, this x right here, and now you have a common denominator of 2x minus 3 to the 1/2 power. So if you raise something to the first power, it's itself. So can you combine some like terms? You have 2x plus another x, that's 3x, minus 3. Okay. And I could probably rewrite this with a radical. Okay, I could rewrite this as a square root of 2x minus 3. So on a multiple choice portion of the test, if this was the question, this is probably how the answer would appear. Let's try the next one. Number 4, y equals x squared times the sine of 2x. If you notice, this is a product, so when you take a derivative, you have to use the product rule. So y prime, the derivative of the first, the derivative of x squared would simply be 2x times the second, right, always plus the first times the derivative of the second. So this problem does two things. It forces you to use the product rule, and to figure out the derivative of this part, you're going to have to use the chain rule. So there's the outside function, there's the inside function. So this part, you take the derivative of the outside, but leave the inside alone, but then you have to multiply times the derivative of the inside. I'm just going to bring the rest down. So 2x times the sine of 2x. All right. So putting all that together, we have 2x sine of 2x plus, I can move this 2 in front because it's all being multiplied, 2x squared cosine of 2x. So this might be an answer choice. Or they might do some factoring. Okay, both terms have a 2x in common. So I could factor out a 2x, now we get sine of 2x. Plus, I've taken out 2 x's, or 2 times x here, there's another x left, times the cosine of 2x. Now this 2x is inside, it's the argument of the trig function, so you can't simply multiply this 2x on the outside and this 2x on the inside. And this is as far as you can go with it. So let's look at question 5 here. Just a little bit of a review. Find the equation of the tangent line. to the graph of this function at this point. Okay. So the good part is I already know the point. The point is 1, -1. But I still need to figure out what the slope of the tangent line is. Well, what would the slope of the tangent line be? It would be the derivative evaluated at this x value. It would be f prime of 1. Before I can find f prime of 1, I first need to find f prime of x. So how are you going to do that? You have to use the product rule because there's a product right there. So x is the first term, all of this stuff is the second term. So the derivative of the first, 1, times the second, 1 minus 2x to the third, plus the first, x, times the derivative of all of this. Okay, so what would the derivative of all that would be? The 3 would come down, the parenthesis stays the same, the power gets reduced by 1. But now I have to multiply that times the derivative of the inside. So the derivative of 1 minus 2x, the derivative of that would just be 0. The derivative of this would be -2. So therefore, f prime of x would equal 1 times all of this, well, 1 times anything is itself. Okay, and if you think about this, you have a 3 times x, that's 3x, times a -2 would be -6x, 1 minus 2x squared. Now you could simplify this if you wanted to, but you really don't need to. Okay? All we really need to know is what f prime of 1 is. So everywhere you see an x, plug in a 1. So if I plugged in a 1 here, 2 times 1 is 2. 1 minus 2 is -1. So that's -1 cubed minus 6 times 1. When I plug 1 in here again, 1 minus 2 times 1. 2 times 1 is 2. 1 minus 2 is -1 squared. -1 cubed is -1. -1 squared is +1, times another 1 is 1, times 6 is 6. So it's -1 minus 6, which is -7. So the slope is -7. As soon as I have this information, I can write the equation of the tangent line. Okay. So the equation of the tangent line would be y minus -1 from there equals -7, x minus 1 from here. These two negatives together, change that to a plus. And this in black, that's the answer I'm going for. Okay. So let's try number 6. What about if they give you data in a table? They tell me what the function is. They define the function as some sort of composition. My goal is to figure out what h prime of 4 is. So before I find h prime of 4, I need to find h prime of x. Well, notice, g is the outside, f of x is the inside. Do not confuse this with a product. It's not a product, it's a composition. So the way we do this is we take the derivative of the outside function, which is called g prime, and we leave the inside function alone, times the derivative of the inside function. I care about what h prime of 4 is. So everywhere I see an x, I'm going to plug in a 4. I'm just going to simplify. I'm going to use the table to figure out what f of 4 is. So here's f of x. At 4 is 5. So I'm going to replace f of 4 with 5 times, what is f prime of 4? It's -1. Now, I now have to figure out what g prime of 5 is. So I'm going to go to g prime, go across where it's 5, and that's -3. So g prime of 5 is -3. So I have -3 times this -1, that's going to give me +3. So that's how you do the chain rule with these things called composition functions. And if you think about it, it's the same thing as like a sine of something complicated or a cosine. We're doing the same things. Derivative of the outside, leave the inside of it alone, times the derivative of the inside. Okay. We got 3 pages of notes today, so lots of examples. All right. So on the back page it says for questions 1 through 3, find y prime. Well, notice here, in number 1, you could use the quotient rule because that is a quotient, but you could also rewrite y just to take what's in the denominator already, and you could move it to the numerator by turning the power into -3, because this 1 here is still 1 times it, and you don't need that 1 times. If it was a number like 2, then you would leave the 2 there, no big deal. So to find y prime here, okay, we treat this as something is getting raised to the -3rd power. So the -3 comes down, the inside stays the same, and we reduce the power by 1. Now we have to multiply times the derivative of this parenthesis. So the derivative of that would be, derivative of 4x squared is 8x, derivative of 6x is plus 6, okay, derivative of a constant is 0. So that would be a first line answer. Okay, if you wanted to rewrite this, okay, you could take this thing right here, move it back to a denominator, because it does have a negative power. So we could move that back to the denominator like that. Okay, so if we wanted to rewrite it, you have a -3, which is like -3 over 1, times this 8x plus 6, all over 4x squared plus 6x minus 7 raised to the 4th power. And this would probably be the answer that's on the paper. Okay. College Board doesn't really like keeping things with negative exponents, so they would probably write it like this, or they could even factor another 2 out of this parenthesis. Okay, so what do I mean by that? If they take out another 2, if you factor out another 2, this would become a -6, and that would become 4x plus 3 over 4x squared plus 6x minus 7 to the 4th power. So they could write it like that. I just took 2 out of this and moved it out front. So let's think about number 2 here. Let's rewrite y. So a cube root is basically saying taking whatever's inside and raising it to the 1/3 power. So I rewrote y. So to find y prime, I can use the chain rule. The 1/3 comes out front. The parenthesis stays the same. We reduce this by 1, so it's going to go to -2/3. And multiply it times the derivative of that parenthesis. Okay. So the derivative of this whole thing, 2 times 2 is 4, so 4x. Derivative of -x is -1. So this would be considered the first line answer. And we can make this look a little bit nicer when we write it. Y prime, we could write it as 1 times 4x minus 1 from this part and this part, because it's really over 1. The 3 is already in the denominator, we can keep it there. And then we can take this thing, 2x squared minus x, and raise it to the positive 2/3 power. Or we can rewrite it as a radical. 1 times 4x minus 1 is still 4x minus 1. Then we have a 3, but we're going to have a cube root. Cube root of 2x squared minus x, this whole thing, to the 2nd power. That's where we get the 2/3 power. So either one of these is probably more likely to be on the test, or to be on the AP test if you get a question like that. All right, so let's look at number 3. Let's write this a little bit different way. So 5 times the cotangent. Now, how could I rewrite this? This is 2 over x to the first. So I could rewrite that parenthesis as 2x to the negative first. So all I did is rewrite y there. When I take the derivative, let's think about taking a derivative. The coefficient always stays. Now that's the outside part, cotangent. What's the derivative of anything cotangent? Well, it is negative cosecant squared. Negative cosecant squared with respect to the same thing, 2x to the negative first. But now I have to multiply that times the derivative of the inside. So the derivative of this, 2 times negative 1 is negative 2. I'm going to make that go down by a power. I can write this a little bit nicer. You got 5 times a negative 2. Okay, so that's going to end up being positive 10. We got a cosecant squared in here. Instead of writing 2x to the negative 1, I can rewrite that as 2 over x. All over, I can move this x to the negative 2 to the bottom and just call it x squared. Okay, so this is probably the way the answer would appear. So I can get rid of this and move it back to the denominator. That's what I did there. All right, let's do the next one. It says if g of x equals the sine of 4x, then g prime at pi over 6 radians, remember that means the same thing as 30 degrees, is what? Before I can find g prime at a value, I got to find g prime of x. So we take the derivative of the outside, derivative of sine is cosine, we leave the inside alone, times the derivative of the inside. So what's the derivative of 4x? Hopefully you say it's just 4. So g prime of x equals, generally we move the coefficients to the front, so 4 times the cosine of 4x. Now, they want me to evaluate this. Okay. So we're going to try to find g prime of pi over 6. So we're going to plug this number in right there. So 4 times the cosine of 4 times pi over 6. Keep simplifying. You can reduce 4 over 6 into 2 over 3. 2 pi over 3. And what's 2 pi over 3? Well, it's 2/3 of pi. Pi is 180, so that's 120 degrees. So if you think about your unit circle, okay, there's 120 degrees. It makes a 60-degree reference angle. Okay, and if you use your fingers, you pull back your 60, and you got one finger over here, and that's the cosine. Okay, but you're in the second quadrant. Okay. So the coordinates there are -1/2 positive √3/2. This is the cosine value. The -1/2 is. So this is going to turn into 4 times -1/2. What's half of 4? It's 2, but you're going to turn it into a negative. So my final answer here is -2. Okay. Problem 5. Find the second derivative if the original function is that. So notice that's a product. So to find the first derivative, we've got to use the product rule. There's the first term, there's the second term. So we say derivative of the first, derivative of 4x is 4, times the second, always plus the first times the derivative. What's the derivative of tangent of x? It's secant squared of x. Okay. Now I'm just going to show you another way you can write that. Secant squared of x is the same thing as saying secant of x in parentheses with a squared there. Goal is to find y double prime. So here's my first term. The 4 is a coefficient, so 4 stays. What's the derivative of tangent? Derivative of tangent is secant squared plus, now I got to take the derivative of this whole thing. Well, this whole thing is another product. So I'm going to have to use the product rule again. So we're going to say first, derivative of, here's the first, here's the second. Okay, so we're going to say derivative of the first, 4, times the second, which is going to be secant squared. So we can write it like that. Okay. Plus the first, 4x, times the derivative of this, of the second. Well, you have to use chain rule here. The 2 comes out front, times secant of x, reduce the power by 1, times the derivative of the inside. So what's the derivative of secant of x? It's secant of x tangent of x. So let's simplify this a little bit. I have 4 secant squared plus another 4 secant squared. That's 8 secant squared of x plus, okay, you have 4x times 2. That's 8x. Let's think about what we have. We have a secant times another secant times a tangent. So I have secant times secant, which is secant squared, times a tangent. So this is an acceptable answer. Okay. Or if you do some factoring, you can pull out an 8, and you can pull out a secant squared, because they both have those things in common. So we took everything out of the first term, so there's an understood 1 there. We took the 8 out, we still need an x. We took the secant squared out, so we still need to write in the tangent of x. So that's the factored way we could write it. And number 6, it says find the acceleration if the velocity is given. So we have to remember that acceleration is the derivative of velocity. Now I might choose to write this a little bit differently. Instead of saying square root of t, I could say t to the 1/2 power plus the cosecant of 1 minus 2t. That's how I would rewrite the velocity. So to find the acceleration, I have to take the derivative of this thing. The 1/2 comes out front. It gets reduced by a power. Okay. Then we have to use chain rule on this part. The derivative of the outside, derivative of cosecant is, remember it starts with a c, so my derivative is going to be negative. Negative cosecant of something, cotangent of something, times the derivative of that parenthesis. So I'm going to keep the 1 minus 2t inside the parentheses to start with. Now I'm going to take the derivative of 1 minus 2t. Derivative of 1 is 0, derivative of negative 2t is negative 2. So here, the acceleration, if I want to write it a little bit nicer, I can say 1 over 2. The t to the positive 1/2 comes to the denominator, which I can also just write as square root of t. Okay, I have a negative here times a negative 2. That's going to end up being a positive 2 cosecant of 1 minus 2t cotangent of 1 minus 2t. If I really cared, I could get that. I could get a common denominator, but that's probably good enough. So I could leave it like that. All right, some more examples here. So it gives me a function. It says find the second derivative. I'm going to start to do these on notebook paper because some of these kind of get long. All right, so this is number 7. F of x equals negative 3 sine of, it says x over 4, which we could also write like this, negative 3 times the sine of 1/4 x. Okay. Let's deal with the first derivative first. So f prime of x, negative 3 is a coefficient, it stays. To get the derivative of this, we have to use chain rule. Derivative of the outside, derivative of sine is cosine, of the inside, times the derivative of the parenthesis here. The derivative of 1/4 x is simply 1/4. Okay, so if I take this negative 3 times this 1/4, that's negative 3/4 cosine of 1/4 x. So that's the first derivative. That's the simplified version of the first derivative. But it's asking me to find the second derivative. So now I have negative 3/4 as my coefficient. Another chain rule problem. What's the derivative of cosine? It's negative sine with respect to the inside times the derivative of the inside. The derivative of 1/4 x again is 1/4. So if I simplify this, I have a negative 3/4 times a negative 1, so I'm up to positive 3/4. 3/4 times 1/4 would be 3/16. So 3/16 sine of 1/4 x, or you could just rewrite it again as x over 4. Or you can write it like this, 3 sine of x over 4 all over 16, because you're still getting the 3/16 there, just like you got there. Number 8 says find g prime at this value. Okay, that's like a negative 120 degrees if this is the function. And this function can be written as secant of x to the 4th power. So if that's what g of x is, let's find what g prime is. 4 comes down, the inside stays the same, the power gets reduced by 1, times the derivative of the inside. So the derivative of secant of x is simply secant of x tangent of x. So I'm just going to write this a little bit nicer. I'll see what we're multiplying. We have secant times secant times secant, that's what that is, times another secant. So we have 4 times secant to the 4th of x times the tangent of x. Now doing this without a calculator, let's write this a different way. Things I know on the unit circle. What is secant? It's the same thing as dividing by cosine. Okay, so that's like saying 4 over cosine of x to the 4th times, what's tangent? Well, that's sine of x over cosine of x. So what does this really mean? This is saying 4 sine of x over cosine of x to the 5th power, because you got 4 there times another one right there. Okay. So let's think about where negative 2 pi over 3 is. Okay. So if I want to think about this, pi is 180. Okay, so 2/3 of 180 is 120, but you're going negative. So here's negative 90. You need to go 30 more. So this is negative 120. Again, it makes a 60-degree reference angle. Okay, you're in the third quadrant, so both are going to be negative. So if I pull back my 60, the coordinates there on the unit circle would be negative 1/2, comma, negative square root of 3 over 2. This is the cosine value. That's the sine value. So you have 4 times the sine value. That's negative square root of 3 over 2 times negative 1/2 to the 5th power. So if we simplify here, 4 over 2 becomes a 2. So you have negative 2 square root of 3 over negative 1 to the 5th power is negative 1. 2 to the 5th power is 32. Okay. Well, dividing by 1/32 is like multiplying times 32. So dividing by negative 1 over 32 is like multiplying by negative 32. So negative 2, that number's outside of the radical, so is negative 32. This times this would be positive 64. So my answer here, without even using a calculator, 64 square root of 3. All right, number 9. It gives me a position function where position is in centimeters and time is in seconds. Find when the particle is moving to the left. I should say when. Find when the particle is moving to the left. Well, what does that mean? That's when the velocity is negative. So before I can figure that out, I need to get a velocity equation. The velocity is the derivative of position. So the 3 comes down, the parenthesis stays the same, the power gets reduced by 1, times the derivative of the inside, using the chain rule. Derivative of t squared minus 4 is simply 2t. So if I want to rearrange some of this, I got a 3 times a 2t, that's a 6t. And then I got a t squared minus 4 squared. Okay. So that's the velocity equation, okay, which really, let me write it another way. So this is like 6t times t squared minus 4 times another t squared minus 4. And for each t squared minus 4, it can be broken up into t plus 2 and t minus 2. So you got a t plus 2, a t minus 2, a t plus 2, a t minus 2, because that's the difference of 2 squares. All right, so therefore you got a 6t, and then you got a t plus 2, but you got 2 of them, and you got a t minus 2, and that's 2 of them. Now, when does it actually equal 0? When is the particle stopped? Okay, so what values of t would make this into 0? Well, what about this one? Hopefully you say, well, at time 0 it would be stopped, because if I plug 0 in for time, this whole thing's going to be 0. Okay, what number plus 2 would give me 0? Negative 2. What number minus 2 would give me 0? Positive 2. We're going to ignore this one. Why? Because time can't be negative. All right, so we're only really worried about positive time values and 0. So the particle stopped at 0, and the particle is stopped at 2. Let's figure out the signs of the velocity. Are they positive or are they negative? So let's test 3 in here. What happens if I put 3 in to this function? 6 times 3, that's positive. 3 plus 2, that's positive. Square it, still positive. 3 minus 2, positive, square it, still positive. So positives, positives, positives. Velocity is positive there. Okay, which means the particle is moving to the right. Now test another one. Test 1. If I plug in 1 here, this thing would be positive. 1 plus 2 is positive. 1 minus 2 is negative, but you're squaring it. So it's like you're getting negative times another negative, which again is positive. So that means the particles, so that we start our stopwatch, the particle's moving to the right. At 2 seconds, it momentarily stops, and then it moves to the right again. So when is the particle moving to the left? Never. Because v of t is never negative. Find the acceleration at t equals 3 seconds. Before I can find the acceleration at 3 seconds, I need to find an equation for the acceleration. The acceleration is the derivative of velocity. It's probably going to be easiest if I take a derivative from that point. Okay, so this is a product, so I can use the product rule. Okay. So derivative of the first, 6, times the second, t squared minus 4 squared, plus, okay, the first, 6t, times the derivative of this whole thing. The 2 would come out front, t squared minus 4 to the first, times the derivative of t squared minus 4, which is 2t. So here's an equation for the acceleration. You could simplify it if you want to, but you really don't need to because they're asking for the acceleration at 3. So everywhere you see a t, plug in a 3. So if you think about this, 3 squared is 9, minus 4 is 5, and 5 squared is 25. Okay. Here, 6 times 3 is 18, times 2. 18 times 2 is 36. Okay. 3 squared is 9, minus 4 is 5. 2 times 3 is another 6. So if we just simplify this a little bit more, 6 times 25 is 150. Okay. Plus, let's see, 5 times 6 is 30. 36 times 30. 36 times 3 would be 72,108. So 1080. So 150 plus 1080 is, let's see, 1080 plus 50 is 1130 plus another 100 is 1230. So 1230, and it's acceleration, so centimeters per second per second. It's a quick moving particle. Number 10 says, here's my function s of t tangent 2t squared plus 1. It's asking me to find the derivative. Okay, so it's a chain rule problem. Tan is the outside function. The derivative of that is secant squared. Leave the inside function alone. times the derivative of the inside. So what's the derivative of that thing? Hopefully you just say 4t or 4t plus 0. So the way we'd probably write it, we'd probably put that 4t out front times the secant squared of 2t squared plus 1. Now number 11 gets a little tricky. H of x equals the sine of 8x raised to the 5th power. Here we actually have to use chain rule twice. Okay, so let's just walk our way through this. We gotta use double chain rule. So if I'm gonna take the derivative, we're gonna treat this thing like the inside. So the 5 gets moved out front first. Then we have sine of 8x to the 4th power. Now I have to multiply that times the derivative of the inside, sine of 8x. So I have 5 sine of 8x to the 4th power, and I can move that 4 there, no big deal there. Times, how do I find the derivative of this part? You got to use chain rule. So derivative of the outside is cosine. All right, times the derivative of the inside, which would just be 8. So if you put all that together, you got a 5 times an 8, that's 40. And you got a sine to the 4th power of 8x. And you got a cosine of 8x. So that's just using the chain rule more than once. It's a double chain rule. Number 12, I get some function, 2 sine of x plus sine squared of x, which again I can write like this. Okay. I'm trying to find where on this function, find the points where I have horizontal tangent lines. And they only want me to concern myself with x values between 0 and 2 pi. Okay, so what does this mean? Horizontal tangent lines. That's where the derivative equals 0, because horizontal lines have 0 slope. So first step, figure out what the derivative is. Okay, so there's the first term. Let's take the derivative of it. 2 stays. Derivative of sine of x is cosine of x. All right, now for the derivative of the next part, you got to use chain rule. 2 comes out front. Power gets reduced times the derivative of the inside. Okay. Derivative of sine is cosine. So if I want to write this a little bit nicer, I can take out a 2 cosine of x. 2 cosine of x, 2 cosine x. So if we factor that out, we would just get 1 plus sine of x. So I need to figure out where this derivative equals 0. Okay, well, it could equal 0 in a couple places. It's going to equal 0 where the 2 cosine of x equals 0, or where 1 plus sine of x equals 0. Okay, so if you want to solve the first part, divide both sides by 2. Right, and ask yourself, where is the cosine equal to 0? That happens at 90 degrees, and it also happens at 270 degrees. Now, let's go ahead and solve this next part. Subtract 1 from both sides and ask yourself, where is the sine equal to -1? that happens only at 270 degrees. Okay, so my possible x values of my points are these. Now, one of them's repeated. No big deal. So far, my x values can be pi halves, or it can be 3 pi over 2. Excuse me 1 second. So we figured out the x values. Now we have to figure out the y values. So I'm going to actually plug these numbers back into the original function. So if I'm going to figure out what f of pi halves is, remember that's 90 degrees. The sine of 90 degrees is just 1. So this would be 2 times 1 plus, again, the sine of 90 degrees is 1, and you square it. So it would be something like that. So 2 times 1 is 2, 1 squared is 1, 2 plus 1 is 3. Now, what about 3 pi over 2? The sine of 3 pi over 2, that's like 270 degrees. The sine of 270 is negative 1. Plus, if I take negative 1 and square it, so this would be 2 times 1 is negative 2. This would end up being positive 1, so that's negative 1. So these are the 2 points on the function where we would have horizontal tangent lines. Very, very long and complicated problem, but if you follow the steps, you should be okay. So let's just check ourselves real quick. Let's just do 2 sine of x plus sine of x squared. Let's do zoom trig, zoom number 7. Now let me switch my window from 0 to 2 pi, because that's the only one we want to concern ourselves with. Okay, so to me it looks like there's a horizontal tangent line right here, and at the bottom of this curve it looks like there's a horizontal tangent line. So hit second, trace, go to option 6, and type in pi halves. To me it looks like that's the top of the curve. It tells me the derivative there is 0, and it tells me the y value there is 3. So I got the right point, and a horizontal tangent line would be 0. Have a slope of 0. And for the second point, same thing. Let's do the same thing. Okay, let's type in 3 pi over 2. Okay, looks like the y value is negative 1, so it confirms that. And the slope there is 0. So my calculus and my algebra were correct. Okay, those are the correct numbers. All right. So this video is getting a little bit on the long side. I am going to make an additional video because it's just a really long note card. And we'll go, in the next video, we'll go over notes for chain rule and double chain rule. Get more practice with that. So I'm going to stop this video right here.